welcome. Today we'll be presenting our second last webinar of this series of the 2025-2026 Transforming Construction webinar series. I'm Brandon Searle. I'll be moderating today's session. As usual, we just do a quick welcome intro to the Research Center as well as Building Transformations, who is supporting this webinar series. I'll then do an introduction to our speaker, Andrew Fisher, who is assistant professor at UNB. Andrew will do his presentation. We'll follow that up with a Q&A and discussion and wrap up. Just a reminder for folks, you can submit your questions anytime using the Q&A feature in the control bar. If you have difficulty hearing, you can check your speaker settings using audio settings. Otherwise, if you have any issues, just send a message in the chat or Q&A or reach out to Roshni and we'll do our best to help you out. Reminder, all sessions are being recorded and will be made available on our website as well as Building Transformations website. And all our past sessions are available on our website as well. If you go to umb.ca/OCRC, you go to events and the TC webinar series, every webinar we've hosted to date is up on there. Just quickly about UNB. UNB is the oldest English-speaking university in the country. It was founded in 1785 and was home to the first engineering lecture in Canada in 1854. I believe it was also the first, or home to the first computer science and forestry schools in the country, and has since grown to be 2 campuses in both St. John and Fredericton, with over 20 research chairs and institutes across the 2 campuses. Just on the OCRC, I could go on about our history, but core thing that I wanted to highlight is our values, which are around industry relevance, collaboration, excellence, and integrity. In our research areas and expertise, so process and productivity improvement and digital tech implementation, some of which Andrew will be talking about today based on his past research, and then structures and building enclosure testing, as well as benchmarking and innovation in construction. The majority of our projects can be found on our website as well, so I encourage folks to go to the research tab on our website and you can check out project profiles there. Upcoming event, we're partnered with Northumbria University in Newcastle, United Kingdom, to host the Transforming Construction with Offsite Methods and Technologies conference this upcoming August. There will be workshops, tours, peer-reviewed papers, and a variety of presentations from academia and industry. I encourage folks to check it out. Registration's open now, and if you were to just Google TCOT Conference Northumbria or TCOT 2026, you'll be able to find the URL pretty quickly. Just a bit about Building Transformations. So they are association, not-for-profit association, headquartered in Canada with activities across Canada and the US. The vision is to transform the built environment through innovation, and mission is foster a community that is committed to knowledge sharing and advancing technology and innovation in the built environment. They have over 1,800 members, over 135 member companies, and they really represent the entire construction sector, right from architects, designers, engineers, planners, right through the sub-trades and the facility managers and O&M teams and so on. Just a quick highlight of the board of directors there. And then our QR code if you're interested in membership. For students, I believe they're free. For folks, you may work at a company that is already a corporate member, so keep in mind that if your company is a corporate member, you also get a free membership if you work at that organization, and then there's individual memberships as well. Recently, they printed the 10th anniversary of the edition of the Innovation Spotlight. So this is a publication. It's available digitally on their website, but you can also order it. I have the latest version here. It actually features some of the projects that the OCRC worked on, where we won a couple awards at the award show last year. Quickly, there's two more in-person events coming up that Building Transformations is hosting in 2026, in addition to their webinars that they host separately. One is in Halifax, Nova Scotia. So the Offsite Construction Research Center is supporting that and organizing a stream focused on modern methods of construction in the industrial, commercial, and institutional construction sectors. This conference is in partnership with Construction Association in Nova Scotia and Building Smart Canada. So the call for presentations is available on Building Transformation's website right now, and I encourage folks to go check that out. The next one is the flagship conference in Toronto in November. So details on that are also available on the Building Transformations website. Just quick thanks to BT's mission partners, and thanks to the OCRC's founding sponsors. All right, and with that, I'm going to welcome Dr. Andrew Fisher, who's going to present on AI-driven construction intelligence from design understanding to manufacturing and optimization. Andrew, if you'd like to share your screen, turn on your audio and video, and we'll be all set.
Perfect. So I'll share my screen here.
Great.
If that's maximized. Okay.
That's good.
Perfect. Thank you for the introduction and the opportunity to present to everyone today. So I'll be talking about 3 projects that I worked on during my PhD in collaboration with a construction company in Manitoba. These spanned across the pre-planning phases of construction projects with the design, material estimation, and manufacturing optimization steps. I'm going to talk about it a bit at a high level. I do have some more technical details here, but I'm not going to dwell on those too much. But for those interested, I'm always happy to talk about this work after the fact. So when we were talking with this construction company and kind of getting the project set up, we found that one of their bottlenecks for actually getting a project is the pre-planning phases. It takes quite a bit of time for design interpretation, estimating those material requirements, and manufacturing planning. So what we wanted to do was develop solutions with AI that could connect these stages more effectively and help increase the productivity, reduce the manual effort, and also improve the consistency across different projects. Because that was another issue that we found, is that there may be different estimators that have different ideas of how many materials are required. Those processes can change over time, and they want it to be consistent across each of the projects. So there were 3, again, main projects that I'll talk about today. The first is building image reconstruction and dimensioning for drawing to 3D visualization. It takes the perspective drawings of a building and produces a 3D envelope of it. We also have jointly trained automation for construction material knowledge, which takes is modeled rather after the equations that estimators have derived for material estimation to try and predict that. Then we also have a panelization algorithm for architectural designs, which looks at optimizing the manufacturing plans for panelization. So the company I worked with was Greenstone Building Products out of Brandon, Manitoba, and the end result that you'll see is that their pre-planning phase is more efficient, explainable, and scalable. So with the first project, and all of these have been published in open access journals, we look specifically at the design phase of a construction project. So what we mean by that is, with the 3D visualization, it's important to produce that to understand client requirements, help support planning, as well as improve the cost estimation. So when we first get those drafts of the drawings of what we want the building to look like, turning those into a 3D model can take a bit of time, and it depends heavily on expert interpretation of the drawings to extract all of the fine details that the client has asked for. And existing methods that do this kind of 3D reconstruction, they work well for more general images that we'll find in literature. So for example, if you have several pictures of the outside of a building, there are methods that can combine all of those perspective and make kind of 3D mesh. But when we look at architectural drawings, they're not specifically designed for that. And with the examples that I'll be showing, we have 5 different perspectives. We have the front side of the building, the right side, the back side, the left side, and the floor plan. And we want to not only project that into a 3D space, but also do it as per the dimensions of the building as well. So we want to preserve those geometric measurements within the drawings and also make it easy to modify after the fact so that it can be kind of changed around or adjusted without much effort. So there are some methods that have been developed for construction projects, but they primarily look at the floor plans only. So you can present a floor plan to the model and it will project the interior of the building as well as the exterior. But you'll see some of the buildings that we're looking at, there can be complex features like stacked openings on top of one another that you can't really get from the floor plan, or angled walls. And that's more difficult to reconstruct from the floor plan alone. So our proposed solution addresses that by using, again, a multi-view. We'll see it's noise aware. And what I mean by that is it knows that we just want, outlines of the doors and the windows and relevant measurements. We don't want any of other symbols that are in the drawing, for example, and geometry preserving framework that takes those architectural drawings and makes it into a 3D representation. So how do we do this? Again, without getting too technical, there's kind of 3 steps that the framework does. So the first is a feature detection part that looks for important structural lines in the drawings, such as, again, the outline of the wall itself, any angled parts of the wall, windows and doors. And then once it's extracted where it thinks those features are, we have what we call a dual branch design that tries to separate those meaningful building features from text and symbols and other visual noise that are on the drawings itself. And we'll see a couple examples towards the end of what I mean by that, but it helps produce a more cleaner 3D projection. And once it has that clean kind of feature extraction from the drawing itself, then it extracts the measurements from the drawings and uses that to scale the features that it's extracted into a meaningful 3D space where we can say that this is n number of feet wide, and that's an accurate representation. So the way that we did that, we used an existing approach called holistically nested edge detection, which looks at extracting edges from different images that you present to it. The approach itself, again, was developed for more general images. If you take a picture of the inside of your house, it can maybe show you the edges of tables and edges of windows and door frames and things like that. But we wanted to modify it to be better suited for architectural drawings. So in the existing approach, they had like a mathematical formulation that when they're extracting these features from the image, they use that formulation to bring all of those features back together. And we instead had the approach learn how to accurately put those back together instead of it being a fixed mathematical approach. We also simplified the input representation. And what I mean by that, and what will be a common theme with these approaches, is that we want to be able to run them locally in-house. We don't want to use any cloud computing platforms or be sending our data off to some company and not know what they're doing with it. We want to be able to run it on pretty modest hardware that's not much cost and doesn't require an internet connection to run. So we found that when we're extracting these features from the drawings, the original approach works with color images. We don't need to consider color at all. It's not going to have any benefits. So our model was simplified to just work with black and white drawings, which reduce the complexity of the model itself. And we went a step further as well to try and, again, minimize the footprint of that model so that we could easily run it even on like a laptop, for example. Throughout my PhD, I worked with a pretty modest laptop that had like some gaming component to it, and it was able to run all of these models itself within minutes. So that was the main focus of it. And And then to get a bit more technical, and I won't go into too much detail about it, this is what you can kind of visualize as the framework's extracting those features out of the image. And you can see this output here is really emphasizing not only the features of the building, but also those features that we don't necessarily need in the 3D reconstruction, like rafters, measurement lines that are below some of the text. So this is just one branch, and then we'd have another branch that tries to text those more irrelevant features to clean it up. So this helps it detect both broader structure and finer building details within the drawings itself. So once we have all of that information extracted, and again, it's doing this for each one of those 5 perspective drawings. Once we have those lines extracted and we have the measurements, now we have to put it into a 3D space. So with these drawings, these are perspective drawings of the building, right? So when you have a front perspective drawing, it's what the building looks like if you stare at it head on. But that's not necessarily what it's going to look like in a 3D space. And I'll show kind of a basic example below here by what I mean by that. But it has to sort of wrap around the floor plan to be accurately projected. So if I show this example here in the top left, you can pretend that this is a front perspective drawing. It's very basic. From our perspective, it looks like wall 1 is 60 inches wide, wall 2 is 120 inches wide, and wall 3 is 60 inches wide. But when we actually push it onto that floor plan, we can see the floor plan has an angle to it. So although our front perspective made it look like wall 3 was equal in length to wall 1, in a 3D space, it's actually along that angle of the floor plan. So we had to take that into consideration when we're projecting it. Within the drawing itself, we would still have those accurate measurements, but in the actual 3D projection, the algorithm had to consider that. So once it's all accurately projected into that 3D space, we've kind of wrapped it around this floor plan accurately. Now we want some way to say, is this good quality? And we don't want to strictly rely on experts for that. We want to try to automatically be able to tell that. So we had 2 measurements. One we called a closest line accuracy. So it's kind of as it sounds. You can see below this basic example, we have a predicted output and what we expected. So in the expected output, we expected an outline of the wall, an outline of the door, an outline of the windows. And in our predicted output, we can see that there's some lines here along the wall that are quite tight to the wall itself. So that's what we call our closest line accuracy. These ones were the closest to the actual lines that we wanted. Then we wanted to also look at what we call noise impact and extra line accuracy. So what we mean by that is any noise or any bad predictions, how much does that impact the visual quality of the 3D model, right? Because that's our main goal, is we want an accurate visualization of the model. So although you can see on the left here where I've circled this kind of cluster of dots and I say it's a higher noise accuracy, that's because visually speaking, if we see that, it's not going to impact the visual quality. They're clustered around a line that we expected. Whereas on the far right here, we can see that there are some stragglers here that are going on to some of the text that wasn't accurately filtered out. That's going to affect the visual quality. We'll be able to see that. So that's how we wanted to try and quantify how good does this actually look. And we'll see some results at the end. I kind of tie all 3 of these projects together, but this is what the whole kind of pipeline looks like. We have those building perspectives, we extract the text, we filter out the features that we want, and then we project it into an accurate 3D space. And again, we'll see a few examples. So now that we've produced a visualization of the building, we want to predict the materials that are required to actually construct it. Of course, this is a very essential part of the pre-planning process. It controls costs, it protects profit margins, it maintains client trust if it's accurate. And we found not only with the industry partner we were working with, but just with the industry in general, it's quite a manual process. There's sometimes in spreadsheets, there's a lot of expert judgment. It can evolve and change over time. And that can make it kind of difficult to scale or maintain that consistency across projects. So there are some BIM-based and rule-driven systems that help improve that. But again, they still heavily rely on predefined formulas, which can evolve over time, as well as that human input. So when we look at some of the literature in computer science that has addressed this, what we found is a lot of them mainly focused on predicting the cost of the building rather than the materials that are required, which you could infer the cost from. And that's not to say that there weren't any that predicted material. It was just the majority of the literature we found predicted cost. And we found that many of them require large, high quality data sets, which is not easy or feasible to get. And they offered limited explainability of how they work. And what I mean by explainability is the ability to understand how did it get from these input parameters about the building to saying that you need N number of panels or X number of screws. It's hard to explain that without having the technical knowledge. So with our approach, we wanted to address those limitations by making it as explainable as we can, and also have it be effective with a limited data set, because it's not feasible to be able to grab these huge, massive data sets about material predictions. So we wanted to work with what we have and try to make it as accurate as possible, which we have a few, again, technical techniques that we did for that, which I won't go too much into the technical parts of it. But the two main approaches that we did was one that was called joint training. And the motivation for this one is that we found many of these building materials that were being predicted depended on the same project information. And we'll see an example of what the company I was working with did. But they had common inputs, such as knowing what the height, the length, the floor area, the number of openings are in the building. So what we did is, instead of having these materials be predicted separately in isolation, we had them kind of share this input space. So anytime height's presented, we included that. You know, if we had, let's say, data points for screws and data points for panels that weren't overlapping, if there were some input parameters that panels could take as an input, we fed that to that prediction model so that it could kind of learn from these other data sets, and again, try to get as accurate as possible. So this allows the model to learn those common building features once and then reuse them across multiple material predictions. And that gave us a more efficient training process, helped make the estimates more consistent, and helped it give us the ability to scale to new materials that may also use those inputs. It would gain that learning from the other material types. So I'm maybe not going to really talk about this, but this is how it works. It's basically, like I said, sharing that learning across these project parameters. So if panels takes heights as an input and screws also takes height as an input, they're both going to learn from each other about how height impacts the prediction of screws and how height impacts the prediction of panels, to give kind of a common representation across those material types. The second technique that we use to, again, try and exploit this learning as much as possible is called cascaded training. So what this exploited is that some material types require the quantity of other material types in order to predict them. Right, so I keep using screws and panels because that's kind of the easiest one, but we'll see in the diagram later all the different types that there are. But if we take panels and screws as an example, to predict the number of screws, we found that in the equation our industry partner had derived, it needed to know the number of panels. So that's, again, something that we can exploit. So since again, we have these data sets that don't necessarily overlap. If we have a data point for screws that, again, takes panels as an input, when screws tries to make that prediction to say, okay, based on these project parameters, I think you need 500 screws, let's just say. If that's inaccurate, the model is going to learn from that mistake. And it's going to go back to that panels input and say, okay, this number of panels that was input, it contributed this much to my error. This value threw off my prediction by, N% or so. With that knowledge of how much it threw off, it can go back to this panels model and tell it, hey, if you provide this input to the screws network, you're going to throw off its prediction by this much. So you need to adjust accordingly and improve yourself to make the overall prediction more accurate. Again, I'm talking at a very high level without getting too much into the details, but these equations are just showing how that connection is made and how that learning from different material types can improve the prediction of other material types as well. And again, I'm happy to talk more about these details if anybody reads the slides later and has questions about that or wants to learn more about that. So what this resulted in was a framework that represents each material type as its own neural network, and then uses the project features that are most relevant to that material. And that, again, was derived from the equations and processes that we had from our industry partner. And like I said, some of these material types were connected to one another because they depend on each other. And the example I've kept giving is panels would act as this kind of macro network, we call it, and it would connect to this screws network, which would be a dependent on it to allow that information to flow between each other. So during the training process, again, our motivation is that we have very limited data. We want to learn as much as possible that we can from this data. And that was the reason we had these different approaches to try and exploit those different relationships. When we make a prediction with the network and we want to tell it how far off it is, we use a simple mean absolute error because an error in either direction is bad. If we overestimate, we may be overcharging the client and might lose the client, or if we underestimate, the company might lose money. So either direction is important, then we want the model to try and minimize that so it gets as close to zero as possible. Now, this text may be a little bit small, but if I just zoom in a little bit here, this example that I've kept giving, panels, for instance, it takes in all of these parameters about the building, the stud spacing, the openings lineals, number of corners, number of openings, the total square footage. And we can see in this data set, we had 776 points to learn from for the panels network, right? And when it produces this output, we can see that it acts as an input to this screws predictor. And the screws predictor, we can see, has 1,573 individual rows to learn from. So what that means is this panels data set, it's not only learning from this 776 instances, it also learns a bit from this 1,500 instances through the screws data set by, again, providing that measure of how much the panels number threw off the screws prediction. And we can see that there's a few other connections here that like butyl connects to spray foam, and bottom split track connects to mushroom head. And there's some that just don't have any connections with each other, but they have common input parameters. Like we can see outside corners takes height, stud spacing in corners, inside corners takes height, stud spacing in corners. So they can share some of the learning with each other to try and produce that accuracy. Now, the last approach I'll show before I dive into some of the results is called panelization algorithm for architectural designs. And this focused on one of the processes that our industry partner kind of specialized in. They had manufacturing plant right by their offices where they produced these building panels. And this panelization process to tell the manufacturing what it needs is important to reduce cost, minimize the material waste, and keep the plans practical based on manufacturing constraints and real-world structural constraints as well. So if we look at some of the literature, there are some rule-based and BIM-driven systems that can automate that layout generation of the panels, but we found that they're often rigid and require a lot of project-specific rules. For our industry partner, we're using a more rule-based system, and I'll show what some of those outputs look like. But it's very difficult because anytime there's a problem or there's an outlier, they have to add a new rule and they have to keep adding these rules. And we'll see that it's not producing as optimal of a result as it can. There were some classical optimization methods that we found, such as integer programming and cutting stock problem that, again, can help with this. But They become harder to apply when the wall shapes are irregular or they have high constraints to them, and we'll see a few examples of those. We did also notice that there were some augmented reality and human-guided heuristics, but that's, again, adding more complexity to the process that some of these optimization methods can't properly handle. So our approach addressed these challenges by treating panelization as a modified 2D bin packing problem, and I'll talk about what that is, and solving it with a genetic evolutionary algorithm that takes into account these manufacturing limits, can handle angled walls, it can handle multiple openings, while still producing pretty good layouts in terms of minimizing the material usage and wastage. So the 2D bin packing problem, I will maybe just zoom in a little bit here to show you. The basic problem is that we have a predefined set of items here on the right side, and we have this predefined bin. And the goal of the algorithm is maximize the number of items that you can fit into this bin, right? So we'll try all sorts of different configurations to try and fit as many of these items into the bin as possible. Now, if we take one step over, as we work towards what we did, now we've modified the problem to say, okay, we have a few stationary items within the bin. They have to sit here, they cannot be moved, and you need to pack your items in around these stationary items. And what we're working towards is these stationary items are windows or doors in the wall that, you know, we're not going to place a panel there. So that's the kind of next step towards what we did is now we have to respect these stationary items. The next step that we take from that is now we have these stationary items and we don't have a set of items defined. What we do have is a minimum width and minimum height, maximum width and maximum height. And we're telling the algorithm, okay, here are your item constraints. We want you to generate the minimal number of items needed based on these constraints to completely fill this bin while you respect those stationary objects like the windows and doors. And that's where we get to our panelization problem. So we're considering the manufacturing constraints, and we're also trying to reduce the number of materials that are required to fill it. So we'll see how we also treat angled walls in the next slide, but this is the essence of the optimization problem that we've derived. So with that problem definition, we then implemented what's called genetic algorithms. So with this type of a problem, it's very difficult to just immediately find a solution, to just say, oh, okay, you need 6 panels of this size, 5 panels of this size, 3 panels of this size, and then you just throw them into the wall and it'll fit. It's actually quite difficult to just come up with a solution. So what genetic algorithms do is, or genetic evolutionary algorithms rather, is that they generate a solution set that works, and then they have what's called a fitness value. And that value is something that tells us in a quantifiable way how good the solution is. And then I'll talk about how we calculate that value. But it generates the solution, says, okay, what's the value? You know, it's 10. You need to get it down to 0. Okay, and then it's going to try generating a new solution that comes from that current one it had at 10. And it's going to keep just getting slightly better and better and better until it converges on a final solution and says, I can't get any better than this. So it also works with 3 different panel types that we had from our industry partner: standard panels, header panels that go above windows and openings, as well as horizontal panels when our width exceeds the height. So with this generative approach, that's necessary when our walls are more complex or have irregularities to them. But for simpler walls, CAD does analyze that. And if it's just a simple rectangle with no openings, it's very easy to calculate what the optimal solution is. So I'm not going to spend too much time again on the more technical details of it, but I just want to show that value and just kind of break that down for you, what it's trying to do. So this fitness value, it's trying to minimize it. Okay, and the way that it minimizes it is it first gets the area of the wall. We just do the width times the height. Then we get the area of the openings. We minus that from the wall. And now we effectively have the area of the wall that we can fit panels into, because we've taken out the openings, those stationary objects, and we have that remaining area. Now, and you'll see in some of the examples what this means, we have this kind of voided area above angled parts of the wall where we shouldn't be packing into midair. We need to pack in the wall, and some of those panels may exceed the wall past the angle, but that's just where a cut's going to be made, and there'll be wastage. So we minus that kind of voided area. Then we look at these panels that it generated and which ones it decided to pack, and minus that from everything. So effectively, we have the area that we can fit panels into, and we're minusing the panels that we have fit into it. And it should be a value of 0, we would expect. If it's packed this wall completely, this first part of the equation should be 0. What we do at the end here is important because we're trying to also not only maximize that packed area in the wall, we also want to minimize the number of panels that we've done it with. So we add on the number of panels that were packed to the end here, and that gives us our final fitness value. So say it's packed 15 panels and it's fully filled the wall, this fitness value would simply be 15. And that approach is going to keep trying and trying and trying to see if it can get lower than 15. And if it just keeps repeatedly coming up with that, then it's going to say, this is as far as I can get. There's no better solution than this. This is what I'm going to output. And just to give you a quick visualization of what that void space means, if we have this angled wall right here, you can pretend that this is an angled part of it. We put these void spaces above to say, like, this is perpendicular to that angled line, and we're filling this error to say you shouldn't pack a panel all the way up here. But any panels that do exceed this line are essentially waste. So we want the approach to try and minimize that as well. Now, if we get into some of the results, which I'll show a handful, there are a lot more in the papers that were published. When we applied BIRD to the different projects that we had available to us, we found that it had a 92.9% accuracy in the geometric representation. So that was that closest line accuracy that I showed. And then when we looked at the noise to see how it affects the visual quality, a higher accuracy in this case means that it's not affecting the visual quality as much. It had around a 78.3% accuracy. So we'll see what that means with the visualizations itself. It means that you can kind of see some of the noise that's come out, but it's not so prominent in general. We found that it had versatility in handling both residential and commercial architecture. And this approach gave some novel metrics for building envelope reconstruction, and brings these models into a quantifiable manner for us to evaluate. So this first building I'm going to show, and it'll demonstrate one of the limitations of BIRD, is this building here. So one of the complexities that you can see on this south or front side here, when I was showing that one example of how when we have that front perspective drawing, we can't tell if it's wrapped around a wall because it's how we're looking at it head on. We'll see how BIRD handles that and is able to project that onto the floor plan accurately. But one of the limitations that we'll see is that this inner wall here is not captured in the reconstruction because it's strictly doing the building envelope. So if I go to the next slide, we can see it accurately captured this kind of corner on the front here by pushing that back onto the floor plan. And we can see it has an outline for that inner wall that it didn't reconstruct. Now, if we want to be picky, we can see some of the little bits of noise here that stuck out that would have brought down that noise accuracy, because we can visually see that. That's I mean, to be dramatic, it's ruining the visualization. It's not accurate. It's something we can see. So that was why we measured that. And you can see its noise accuracy here was around 79%, which is a bit more visible to us. Now, if we go to one of our more complex buildings. We have this one, which has this wrapped around wall here, which we'll see Bird does struggle with a little bit, but it does reconstruct it. We have a lot of these angles along the wall itself. It's quite complex. So this is the reconstruction that Bird did, and it is a bit hard because it's kind of see-through, so you can see through to some of the walls, but you kind of get the idea of how it did its reconstruction, while also seeing some of the noise that came out of those harder geometric areas. So this one gave a bit more difficulty to the model, but it was still able to produce a somewhat accurate representation of it. Now to show you just one perspective, because that's the whole final output. This is an architectural drawing of one of the buildings that we're looking at. And I want you to look in the center here with all of these measurements and symbols and lines. We'll see Bird in general does a decent job, but it does start to struggle around these more kind of clustered areas. So each one of these black dots that you're seeing are at the start or end point of a line that is extracted. And you can see around this window area here, and we've increased the size of the dots to make it a bit more dramatic so that you're able to see it better. But we can see it had a hard time around these measurements and getting them out. But in general, it did a decent job. It does get this kind of outer and inner measurement of the line, so then we can get something kind of in the center to be close to where the actual line is. Now with the Jack approach that looked at material estimation, we compared that to basic regression models, and we had 14 different material types. It outperformed those regression models in 8 out of the 14. And in some of them, it had a pretty good reduction of the mean absolute error. For example, with screws, it had in comparison to the regression models, a mean absolute error difference of 523 screws on average. We did also not only use the estimation data, we tried using some synthetic data that was generated based on the data that we had. We also used shipping data to have more accurate numbers. And in the paper, we showed that our framework was able to learn more effectively from the shipped data, which just shows that data kind of made more sense for the project parameters. When we look at some of those performance gaps in these remaining 6 materials, we found that there was sometimes data scarcity in them. For example, one of the ones is this below grade track data set. We only had 56 rows to learn from. And that's just not enough for these algorithms to learn. Some of them had a lack of dependency links from other materials, so it couldn't utilize that extra learning. And some of them had a very, very minimal mean absolute error difference. And the benefit with our approach is that it can learn and adapt over time, whereas the regression models are more fixed. So we showed that Jack successfully learned those intermaterial relationships and help produce more consistent material estimations as well. With the last approach, PAD, found that optimizes manufacturing efficiency, and I'll show a few real-world examples. But when we look at the software that our industry partner had that they developed, it outperformed it in 22 out of 24 scenarios that we presented. And outperformed in this case means it had a lower number of panels in its solution that it generated. Again, for those remaining 2, it wasn't like a crazy difference or anything, but it was outperformed by the software in those 2 scenarios. When we look at those 22 that it did better on, we also had expert annotation. And out of those 22, our approach surpassed 10 of the expert results by having a lower solution as well. So we showed that PAD effectively connects that estimation and fabrication, uses that early project information to create practical panel designs. So if we look at an example, which this is again a bit more of a complex one, it has that angled wall, it even has angled openings. When we look at the solution from our industry partner software, it produced one of 45 panels. The expert solution produced one of 25 panels, and then PAD produced a solution of 22 panels. So it was able to, again, reduce that material wastage while still respecting those complexities with the wall itself. If we look at this other project, which has a bit of, again, a different geometry, the solution produced by the software was 14 panels. The expert solution was 15 panels, so they actually came up with one that was one more than the software, while PAD came in with a solution of 13 panels that it was able to accommodate. So again, that's an approach that just takes that information about the building as an input and then works towards this solution over the course of maybe a minute or so to come up with that optimal solution. So looking at the future directions for this work, we, of course, would like more data to enhance the scalability of these frameworks. That's easier said than done, but that is where a lot of this accuracy comes from. I also want to look into integrating this into an end-to-end automated workflow that connects all three of these approaches. So you just need to provide the drawings as an input, maybe a couple building parameters, and it does all three of these steps for you. And also working towards making them more interpretable and being able to understand the outputs of them. We tried to do that with Jack by modeling them after the equations provided to us from the drafters, but still it can be a bit difficult to understand how it gets from the input to the output. So we want to work towards that, as well as emphasizing, since data is such a constraint in this area, synthetic data generation, and benchmarking against standards that are already established to help with the reproducibility and sustainability of these applications. So all of that, we also need, of course, collaboration. It's not something that you can just do in a lab. And also integrating it into BIM systems would help pave the way for using these construction practices. These are all of the papers I've referenced, and that is the presentation. Thank you.
Great. Thank you for that, Andrew. It was really interesting, and it was pretty cool to see how you took a pretty complex concept and were able to present it in a way that many of us would be able to understand. Just a reminder for folks, if you have a question, you can submit through the Q&A. I have a few to get started, and we have about roughly 10 minutes for Q&A.
Sure.
So, Andrew, I was a couple of weeks ago, I was at a conference focused on digital technology and construction, and I mean AI was what everyone was talking about, and a lot of I know. So actually, before I get into this, what was the time frame that these projects took place? Like, what year to what year?
So for the core components of it, it was approximately a 3-year endeavor. I was the only student working on it, and then for another 6 months or so, I worked on developing an interface and making it a bit more usable. But the core research itself is about 3 years.
Yeah, so was that like 21 to 24 or 22 to 25?
21 to 24, yeah.
Cool. Yeah, no, the only reason I ask is so a lot of the discussion when we were at the conference, it was about the buy versus build versus collaborate type of approach when it's between contractors or manufacturers and software companies or technology providers. And the industry seems to have evolved a lot in terms of what solutions are available. I'm curious to get your thoughts on, like, where did, for companies, manufacturers, et cetera, that are starting to explore this, what do you think is the best approach? Because a lot of them have nuanced manufacturing processes. They have certain ways that they do things. They have certain ways they set up their designs when they go from, the BIM model to shop drawings or vice versa to the factory. What would you kind of recommend companies do, or is it better to start looking at off-the-shelf products because this industry seems to be moving so quickly?
Yeah, no, like you kind of said, a lot of the processes are very specialized or specific to the company themselves. I found that a lot of the off-the-shelf solutions don't generally work in every use case that companies would need it for. And the development of these projects, for an AI system requires a lot of kind of expert input or somebody who's in the computer science field, for example. I feel like personally, something like this, having a master's student or a PhD student in a collaboration with a university partner is probably the way to go to get a solution that works for the company, and I would say is also sustainable for them too, to be able to provide funding for a student for 2 years or for a PhD student for 3 or 4 years. I'd honestly feel like that's the best way to go to get something that works specifically for their solution and is something that will be maintained over time as well.
Well, yeah, no, for sure. That's been our experience, I guess, as well with a lot of our R&D projects. It's like you kind of do this review of what's available publicly, but then it does get into like the implementation phase of the tool, and then the O&M, or the constant maintenance of the tool
Yeah,
afterwards. And I guess I was going to ask about that. I had to take a call, so sorry if you did touch on this, but I had to take a call for a sec while you were
obviously.
presenting. Did How has the company, or where are they at with using it day to day? Were they ready to implement it, or is it kind of like they have it and when timing is right, they're going to take it and implement it? And then, like, I guess who within the company was kind of like the subject matter expert spearheading? Because in my experience, you need kind of a quarterback in the company that you're collaborating with, and you need, the researcher and the faculty member kind of supporting it as well.
Yeah, no, and that is one of the biggest difficulties, I would say. It is more, I believe, on the latter, that they're waiting for the right time to start using it more regularly. What I did in the last 6 months of the project, so after I was done that main kind of research component and develop these solutions, was that I focused on making it as usable and accessible to their tech team as I possibly could. So they had bought a basic server in-house that could run this. I worked on developing a basic kind of web interface where they could interact with it quite easily just by uploading drawings to it, maybe providing some information about the building parameters, as well as commenting in the code and documenting as much as I possibly could. And I left that with the tech team that they have in-house, who didn't necessarily have AI expertise, but the way that I left the system with them was with a lot of documentation that somebody could read and kind of understand what is happening in different components of the code, as long as they have some software development experience. But I do think having it actually used day to day is one of the biggest challenges, because it's kind of, if the approach is already working, then why change it?
Yeah.
Even if there are some benefits to it, there's still some risk. Is this actually going to be productive for us to abandon what we've been doing and has been working? So I feel like that's a challenge in of itself. But with the company, that's as far as I know where it's at for them right now.
Yeah, for sure. Like you start to see some startups in quotes. I don't know if they're quite classified as startups, but some younger companies who are implementing new tools like this from the onset. But the mature ones who really understand their business and have some expertise in house, that it's kind of all in their like, it's like their estimator, they know how to do it, but it's all that knowledge is in their brain based on
Yeah.
history, right? Or their plant manager or factory manager, or their on-site foreman, or their design engineer or whatever. It's all knowledge in here. And I guess that gets to like the whole um, value of doing it, of like, as the next generation retires and as there's a labor shortage, and that those skills may be lost, how can digital technology support that transition? Um,
Yeah,
yeah. So,
yeah, definitely.
yeah.
I think a lot's in just demonstrating it too. Like, so I mean, we had a small set of projects, but I maybe feel like, with the work that I was doing, it was over the course of a PhD, and I wrapped up what I needed to do with the PhD. But I would say if there could be maybe another student beyond that could just keep using it to show the results. Maybe that would help over time, showing that this could actually work. It's just having that kind of push, I think, is what's needed.
Yeah. How involved was the team that you left all the documents with? How involved were they during the project?
So from a AI perspective, I was the expert on that. That was solely my responsibility to do that research, talk with my supervisors about it, and produce those results. But the tech team provided support in terms of access to servers or access to data sets, documentation from their end, getting some of those expert inputs, for example, from the panelization algorithm. They help coordinate that. So no, I mean, without them, it wouldn't have been possible. They really helped with that data access and telling us, or getting the right people to tell us if these outputs are good, or if this is going in the right direction that they want. They were kind of the coordinators for that. So they're very, very much helpful. Yeah.
Yeah, no, that's awesome. Yeah, sometimes getting that buy-in from the company, like human resource and that human knowledge to provide just feedback is a huge value
Yeah.
to ensuring that like the project is a more applied research rather than stuck, so to speak, in a theoretical world.
Exactly. Yeah.
Yeah. No, that's great. I'm just mindful of time, so I'm going to leave it there. For folks who are interested in reaching out to Andrew, obviously his email's there, andrew.fisher@umb.ca. We hope to have Andrew involved in some projects at the OCRC as well. So if you are working with us already and you see an opportunity for this, definitely reach out to. Feel free to contact myself or Andrew or anyone of the OCRC team. And I'm just going to share my screen quick. So our next presentation is coming up in May. Keep an eye out. The date is not the third Thursday of May, just because we're going with the speaker's availability. But his name is Maxime Pelletier, and so Maxime works for a company called Utile in Quebec. They build student housing. They're a nonprofit organization that builds student housing. They recently built a 6-story volumetric modular project, and they had a company who documented all the costs and materials and everything throughout the process so they could do a deep dive case study on the project. And I saw parts of this presentation in a webinar in February, and I think it'd be pretty valuable to promote and talk about. So keep an eye out for that. It will be, again, a case study done by Utile. They have collected a ton of data on the kind of pros and cons and what worked and didn't work and the costs associated with the project compared to conventional and so on. So encourage folks to check that out. And with that, I'll just remind everyone to, if you need a certificate of attendance, if you're, a professional engineer or a licensed architect, or, your profession requires this for professional development hours, just scan the QR code, fill in the form, and we'll make sure you get a certificate before the end of the calendar year when you renew your license. So thanks again to everyone, and we'll see you next time.